third, sorry. So here again, let me read the question. It says 15 grams of anhydrous sodium thiocarbonate 4 having some impurities were made up to 250 cm of solution. 25 of this solution neutralized 24.5 of 1 mole HCl. We should calculate the percentage of impurity. So let's take it from the beginning again with our given. Okay, question number 3. Is it 15 grams of anhydrous sodium thiocarbonate 4 having some impurities were made up to 250 cm3. So sodium thiocarbonate 4. Let's call this, it's always B. Let's put it that way. Sodium thiocarbonate 4. We have 15.0 grams of this in 250 cm3. So we say 25 cm of this solution neutralize 24 of the acid. So this is acid. Okay. The volume of the acid is 24.5. Volume of acid is 24.5 cm3 and the acid is HCl. And the volume of the base VB is 25 cm3. Now, therefore of 1 point, okay, the molar count of the acid is 1 mole. Ca is 1 mole per GMP. So from here, we should calculate the percentage of impurities. Remember, they say 15 grams of anhydrous sodium thiocarbonate 4 having some impurities were made up to 250 cm3. So the 250 cm3 here and the 15 grams, we use it to get our mass concentration, which is mass over volume in dm3. So, and this mass concentration we're getting here is that of what? The impurity. Now, we are bound to calculate that of purity when the time arises, because we are going to calculate percentage impurity. But before we proceed to that, we have to get our Na and our Nb through the balance of the chemical equation. Na, sorry, this is this. Nb, Na. So I have disodium thiocarbonate 4 plus HCl. That will give me sodium chloride plus CO2 plus water. Now let's balance. We have 2 sodium here. I have 2 hydrogen. There is 1 here. If I put 2 here for hydrogen, hydrogen is balanced. And here I have chlorine 2, so I can put 2 here. I think that's 2. Okay, by so doing, mole ratio of the base is 1. That of the acid is 2. So I can take out this. Remember, the state is aqueous, gas, liquid. So that is that. So let's proceed. What next do they want? They say we should just calculate the percentage of impurities. Wow. So for us to calculate the percentage impurity, we are dealing with the base. We need to know the molar concentration of the base. So we use the formula molar count times relative molecular mass to get the mass count of the pure sodium carbonate before we can proceed to get all that they are asking of us. So from here now, we will therefore go direct to get the molar concentration of the base. Although it's not asking, they are asking a percentage impurity. You can't get it without doing certain other things. So we're going straight to do that, to get the molar count of the base first. A molar count of B. We get it using the formula CAVA over CBVB is equals to NA over NB. We are looking for concentration of the base. So I call it CB is equals to CAVANB over VBNA. And this is equals to the concentration of the acid is given to be 1.00 mole per dm cube times volume of the acid is 24.5 cm cube times number of moles of the base NB is 1 all over the volume of the base is 25 cm cube times number of moles of the acids Na is 2. So cm cube goes with cm cube. Let's proceed to see what we have. 1 times 24.5 times 24.5 is equals to this, divided by 25 times 2, 50, 0.49. So this is 0.49 mole per dm cube. That is the molar count of the base, CB. CB is 0.49 mole per dm cube. So we've gotten our molar count of the base. So now the next thing is we have to get the mass concentration of pure sodium thiocarbonate 4. Yes, so let's proceed. Then I call that B. Now, B, mass count of pure B is equals to molar count of B times relative molecular mass of B. And this is molar count of B is 0.49 mole per dm cube times relative molecular mass is 106 g mole. So this is equals to, let's see, 0.49 times 106, 51.94, that's very high. 51.94 GDM cube of pure B. Now, if we've gotten pure GDM cube of pure B is equal to 51.94. What about that of mass concentration of the impure? Let's find out. So this is B, let me call that C, mass concentration of the impure. Mass count of impure B will be mass over volume. Mass in gram over volume in dm cube. The mass is 15.0 gram over the volume is 250 over 1000 in dm cube. And this is equals to 250 divided by 1000, 0.25. So 15.0 gram over 0.25 dm cube is equals to 15 divided by 0.25 is 60 GDM cube. Okay, we have the mass Cont of impure, of impure now. GDM cube of impure is equals to 60. Then the question says percentage impurity. We are going to get the percentage purity first. From there we get the other one. Okay, let me call that D. D says percentage impurity. Sorry, purity. Let's call it purity first. Is equals to the mass Cont of pure is 51.94 GDM cube over the mass Cont of impure, which is 60 GDM cube times 100, and that is equals to 51.94 divided by 60 times 100 give us 86.6%. 86.6%. Therefore, percentage impurity is equals to 100 minus purity, which is 86.6, and that is equals to 13.4. That is 13.4%. So the amount of impurity was very small, which is 13.4. The substance is 86.6% pure. So that was a good one. That is our third question. Let's take our fourth question here, which probably should be our last. Alright, let me take out this. "12 grams of a mixture of anhydrous sodium trioxocarbonate 4 and sodium chloride. Be it a mixture means that it is impure." So that 12 gram and sodium chloride were made up to 1 dm cube. So the mass concentration of the impure sodium trioxocarbonate 4 is 12 GDM cube. So let's start the base first. And, okay, 12. Now, 25 of this mixture of B were neutralized by 20 of 0.2 mole HCl of A. So there's acid here, which is HCl. And the concentration of the acid is 0.2 mole per dm cube. The volume of the acid is 20 cm cube. Now, for the base B, disodium triiodocarbonate 4, the mass GDM cube, the mass Cont of impure is 12 GDM cube. Now the volume of the base VB is 25 cm cube. And order. Let's say we should calculate the mass of sodium chloride impurity. That's the percentage impurity. Find also the percentage purity of the trioxocarbonate 4. So we're going to get the percentage purity and impurity. So before we proceed further, remember our usual, we have to balance the equation so we'll be able to establish the number of moles of acid and that of base. So let's call this our Na. We don't know what it is. Nb, we still don't know what it is. So let's balance it. It's HCl plus that is sodium trihydrocarbonate 4 will give us sodium chloride plus water plus CO2. 1 chlorine, 2 this, 2. I have my 2 here. I have 2 here. Are we good? Yeah, I think so. I have 2 chlorine, 2 sodium, 2 sodium. That's good. Aqueous, liquid gas. Number of moles, Na is 2, Nb is 1. They are asking us to get the percentage, purity and impurity. So before we do that, that which is given, the mass concentration there is for the impure sodium trihydrocarbonate 4. So we have to get that of pure by using the formula molar Cont times relative molecular mass of B. But before we proceed further, we have to calculate our CB, concentration of the base, so that we can use that formula. So let's start with that. Okay, let's call it A. Molar count of B. We use the formula CAVA over CBVB equals to Na over Nb. CB is what we're looking for. So CB is equals to CAVANB over VBNA. And this is equals to Ca is 0.2 mole per dm cube, times Va, volume of the acid is 20 cm cube, times number of moles of the base is 1 over volume of the base is 25 cm cube, number of moles of the acid is 2 cm cube. Will cancel this. So our answer here for concentration of the base will be 0.2 times 20 divided by 50, which is 25 times 2, 0.08. 0.08 mole per dm cube. 0.08 mole per dm cube. So now we've gotten our our CB. Ca is already given. So from here we have to get the mass concentration of the pure salt, which is the base. And that can be gotten by multiplying the molar count times relative molecular mass. So let's call that B, mass count of pure. B here, mass count of pure B, which is equals to molar count of B times relative molecular mass of B. Molar count of B 0.08 mole per dm cube times 106 g mole, which is the relative molecular mass of the base. If you calculate this, 23 times 2 plus 12 plus 48, which is 16 times 3, will give us 106. So when we multiply 0.08 times 106 times 106, we get 8.48. Okay, it's less than that. Okay, that was good. GDM cube of pure is 8.48 GDM cube. Now we're done with all that. Let's move straight to the question which they ask of us. We have to do a lot of things in order to get what we want. We must get ourselves acquainted to that. Now, percentage purity, C. Percentage purity is equals to mass count of pure, which is 8.48 GDM cube, over mass count of impure, which is 12 GDM cube, times 100. And that is equals to 8.48 divided by 12 times 100. 70.7. This is 70.7% pure. Therefore, percentage impurity is equals to 100 minus 70.7, and that is equals to 29.3. That is 29.3%. That's our fourth question. I think we should take one more. Should we?
Yeah.
Okay. The fifth and the last question for the day. It said A is 0.105 mole of HCl. The law of HCl. A, HCl. Okay. A is 0. Okay, the concentration of the acid 0.105 mole per dm cube. B contains 6 grams of baking powder per 100 cm cube of solution. In B, the NaHCO3. They say it contains 6 grams in 100 cm cube. This is mass quantity of impure baking powder. We'll find out. In a titration, an average of 27.48 of A, volume of the acid is 27.48, 27.48 cm cube. Neutralize completely 25 of B. Volume of the base is 25 cm cube. Okay. Write a balanced equation for the reaction. That is A. Okay. A is write the balanced equation. So we have HCl plus sodium hydrogen tricarbonate 4 will give us sodium chloride plus water H2O plus CO2 gas. Okay, now let's look at it. We have hydrogen 1, 2. We have 2. Oxygen 3 here. 2 plus 1, 3. Sodium is 1. Sodium is 1. Chlorine is 1. Chlorine is 1. So we are good. So the number of moles of acid is 1. Number of moles of base is 1. Let's leave the equation there for now. Yeah, I think we're good. Okay, next thing. Calculate the concentration of the base, that is sodium hydrogen tricarbonate 4 in mole per dm cube. They want us to know the molar count of this side. Now, we use our CAVA formula to get that. So I call this CB. I don't know, so that is our B, molar count of B. We use the formula CAVA over CBVB is equals to NA over NB. And CB, which we are looking for, CB is equals to CAVANB over VBNA. This is equals to concentration of the acid is given to be 0.105 0.105 mole per dm³ times volume of the acid is 27.48 cm³ times number of moles of the base 1 all over volume of the base is 25 cm³, number of moles of the acid is 1. So let's proceed. 0.105 times 27.48 is equals to this, divided by 25, divided by 25. 0.115 mole per dm³ of B. So I come back here, 0.115 mole per dm³. So if that's true, let's look at the next question. Okay. II says we should calculate the amount of sodium hydrogen trioxocarbonate 4 in 100 cm³ of B. Now, amount is molar count times volume, and the volume they give us is 100 cm³. Yes, amount 100 cm³. So we have to now bring amount in of the base. So that's why we calculated this for, so it will help us. So C, we call it amount. C, amount of B is equals to molar count of B times volume in dm³. So let's see, the molar count of the base is 0.115 mole per dm³ times the volume that gave us 100 over 1000. We have to convert it to dm³. Okay, now we have 100 divided by 1000, 0.1. Good. So this is equals to 0.115 mole per dm³ times 0.1 mole, 0.1 dm³. So this was what? 0.1 times 0.115 will give us 0.0115. 0.0115 mole. So let me put it somewhere here. Amount 0.0115 mole. So I can take this out. Now we've got an amount. Okay, amount of B. Now, volume of carbon 4 oxide produced from 100 cm³ of solution B. Okay, mole concept is coming in. Now, volume of carbon 4 oxide. This is the carbon 4 oxide of B. This is our B. They say of 100 cm³ of B. Okay, yeah. From 100 cm³ of B. So from here, we have 1 mole of this is equivalent to 22.4 dm³ of that. And 1 mole here, now 100 cm³, 1 mole here is equivalent to 22.2. So don't forget that, which is, okay, let's use amount. We've gotten the amount of this, so we can use amount with that. Alright, that's good. 1 mole of this is equivalent to that. Then 0.0115 mole of this will give us X. That's more concept. I will have a class on that. So this is x is equals to this times this in dm cube, or we'll convert that to cm cube, anyone, times 22.4, 0.2576, 0.2576 dm cube, or times 1k, or 257.6 cm cube. So these two answers are correct. This is in dm cube and this is in cm cube. That is the volume of the gas, that is the CO2, in 100 cm cube of this. Now let's proceed. Now the last one is percentage by mass of sodium hydroxide carbonate 4 in the sample. That's the percentage impurity. Now, the percentage impurity, what they give us here, this is what we have. This will give us the mass count of the impure sodium hydroxide carbonate 4. But we have to also calculate the mass concentration of the pure sodium hydrogen carbonate 4, so that we'll be able to get our equation. Now, let me clean this equation of reaction now. Now, mass count of impure, let me calculate that first. Okay, let's just put it that way. Mass count of impure B is equals to mass over volume. Mass in gram over volume in dm cube. Which is, mass is 6 gram over 100 divided by 1000, which is 0.1 dm cube. And this is equals to 6 divided by that. First of all, 100 divided by 1000 is 0.1, that's correct. So 6 divided by 0.1 will give us 60. Wow. 60 GDM cube of impure. So we have 60 GDM cube of impure B. So let's look for pure. Now, mass count of pure B is equals to molar count of B times relative molecular mass of B. The molar count of B, Cb, is 0.115 mole per dm cube. The relative molecular mass is of NaHCO3. We're going to calculate that right now. 0.115 mole per dm cube times 23 plus 1 plus 12 plus 16 times 3. So 16 times 3 is 48. 48 plus 13 plus 23 is 84. So I have 0.115 mole per dm cube times 84 g mole. When I multiply that times 0.115, 9.66 GDM cube. Remember I told you earlier on, the mass count of pure must be less than that of impure. So here we have 9.66 GDM cube of pure B. So now let's proceed. Percentage purity. Now, the percentage purity is equal to mass count of pure 9.66 GDM cube over mass count of impure, which is 60 GDM cube times 100. 60 divided by 60 times 100. 16.1. This is equal to 16.1%. That's very, the purity rate is very small, so the percentage impurity is very high. So now let's finalize. Mass count, okay, percentage impurity now. Percentage impurity is equal to 100 percentage impurity is equal to 100 minus purity, which is 16.1, and that is 83.9. 83.9%. So we've done justice to all the questions required. Don't forget, percentage purity is equals to mass count of pure sample over mass count of impure sample times 100. From there, percentage purity plus percentage impurity equals to 100. You cannot always make the change of subject to get what you want, like we've just got to right now. So this is the end of the class. Thank you and have a nice day.